Yeah, so basically the presentation I'm going for is a look at the applications of some of the control stuff, and hopefully we can have a discussion of applying the formal methods. But there's a review paper that was recently released, and it's written by one of the top researchers in this field, Hassan Bevrani. So the title of the paper is Power System Frequency Control, an updated review of current solutions and new challenges. So to just give a high-level overview of the power grid, those that have heard me talk about stuff before will probably be familiar with this. But in general, you can describe the power grid as basically generation, which is power going into the grid, and loads, which is power going out. So the generation would be your typical power plants and your renewable energy, and the power out would be stuff like the lights for your home or charging an electric car. The frequency of the power grid is the balance between this. So you can see this kind of nice scales diagram here. And in the UK, that kind of balance should be around 50 hertz. And in other countries like the US, they try and balance things at 60 hertz instead. So the frequency is actually the kind of physical representation in a way is the rotation speed of generators which are in these power plants. So then talking about frequency stability, from this paper they give a nice definition, which is frequency stability is the ability of an electric system to regulate its frequency within a permitted nominal operating range. So you want that balance, and you don't want it to sway too far to the generation side or too far to the load side. So frequency instability, therefore, is often resulted from a serious imbalance between the total generation and the total load. If you've got too much load, the frequency will massively veer off to one way. And this leads to various different problems down the line, such as blackouts. Because of this, the frequency stability is also directly associated with that rotor speed, which we talked about. The frequency is the generator rotor speed. So that leads quite nicely onto the current challenges. So there's two main challenges which we're seeing in the future of the power grid. The first one is the reduction of system inertia. So the inertia is, in essence, it is the inertia of that physical turbine which is spinning. And that's reducing because we're adding more components like renewable energy into the grid. So the typical approach, the centralized approach, would be a power station which has this inertia spin. It provides power, and then different loads such as houses, factories, buildings will take it. However, the future has solar panels, wind power plants, all these different devices, electric vehicles in the load, and there's a lot more going on. And because the renewables are replacing synchronous generators and power stations in some cases, we're seeing a reduction in the inertia. And the inertia is very important because it manages the rate of change of the frequency. So a lower inertia will make the power grid more volatile. The second main challenge is that the renewable power production is quite variable. So you can imagine the cloud cover goes away, solar panels will produce less energy, or the wind will change and the wind turbines will either suddenly increase or suddenly decrease in power. And that reduction of system inertia, coupled with an uncertainty of the replacement, means that you can get some quite violent changes in the power grid. So what are the solutions? There's kind of two main solutions which are mainly being proposed. The first one is emulation of inertia and active power injection. So this comes from the idea that these new devices, renewables, actually can respond a lot faster to changes in the frequency compared to a synchronous generator. Instead of taking a while for a turbine to speed up, these devices can quite quickly inject some more power. And virtual inertia is a clever concept which tries to resist against that loss in inertia from less physical power plants by having batteries and control to act and do the same thing. The second thing is demand response. So this involves controlling the loads rather than controlling the generation. So when the frequency changes, rather than changing the speed of the turbines, you can actually try and reduce the amount of loads on the system or increase them in order to balance it from the other side. However, with all of these components, they have quite a high amount of communication devices and devices connected to the internet, such as the Internet of Things. And so this actually means that the cyber attack surface area is increasing, and frequency response is a critical part of the grid, and it makes it a very prime target for cyber attacks. So the common research focuses in this field, therefore, there are two main ones really. The first one is the frequency response itself. So you can see in the green boxes, you've got things like the steady state behavior, the frequency nadir, which is basically the lowest point that the frequency falls to, and then also the rate of change of frequency, which is the speed in which the frequency will change over a short period of time. The rate of change of frequency is particularly related to that inertia value that we talked about before. And so here in the diagram, you can see that there is a response with virtual inertia and a response with no virtual inertia. And you can see that actually this idea of virtual inertia can improve the response of the frequency so that the reduction in frequency nadir is smaller. Other elements which people like to focus on are the nonlinear ones. And this can be the generation rate, the dead band, and time delays from communication in the system. In terms of uncertainty, there's two main types which will affect the power grid. The first one is time delays, I just mentioned. So this will come from communication channels, both open communication channels and dedicated channels. The communication time delays degrade the frequency dynamics and can even lead to frequency instability. In essence, you send a signal and it takes too long for it to arrive. The other uncertainty is parameter uncertainty or structural uncertainty. And so this is more around the noise in the system. So this is where robust control theorems, like we've talked about for a few weeks before this, come in handy. So stuff like model predictive control, the Riccati equation approaches, Lyapunov stability theory. I'm sure I'm butchering some of those names. So in essence, what this paper talks about is two kind of main areas then for research. On one side, you've got analysis. So this will involve kind of modeling a system. It will involve the policies, you know, at what point should load shedding occur. It will involve modeling the physical constraints. So actually trying to work out the effect of the inertia, the time delays, the dead band, but also some emerging concepts and new systems, such as the energy storage systems, the electric vehicles, and virtual inertia. On the other side, you've got the synthesis. And so this will involve mainly just the frequency control techniques. So in the diagram in the right, in the bottom right, you can see the primary frequency control is the kind of first control, which happens over a period of a few seconds. Then you've got secondary frequency control, which is over a longer period of time. And finally, you've got the tertiary control, hard word to say. And this will basically be the late stage in the control, for trying to bring it back, and will involve stuff like any power responses you have, which aren't currently connected to the grid, but you connect in order to fix quite a serious issue. So the conventional frequency control has four main steps. The first one in green is the primary control. So this is during a normal operation, you'll get some small frequency changes and you just compensate those using the droop over a few seconds. The second one is for slightly more abnormal operations. So this will be activated to compensate any slightly larger changes in the frequency and try and return those values to the nominal value over a few minutes. Thirdly, you've got the more serious faults, and these can cause quite significant load generation imbalances. So to reduce the risk of failures, power reserves will be disconnected or connected to the grid in order to provide that change in frequency that's needed. And finally, the last one, which is the worst case scenario, is the emergency control, which is where load shedding events will happen and other protection systems are activated. In terms of non-conventional frequency control, things we're likely to see in the future, there's 4 of these. So the first one is the idea that actually the renewables can act as the distributed generators. So these can provide primary frequency control, secondary frequency control, and inertia control on their own. So for example, the solar and wind farms can respond within seconds, and renewable devices which have inverters in them can change their set points and provide a certain amount of frequency, a certain amount of power that's required to stabilize the frequency. So an inverter-based renewable, basically, it could be a wind turbine that has, say, a battery connected to it. So it can inject some extra power from its battery, or it can store some to reduce the amount it's providing. Another example is that wind turbines can actually be decelerated, and the rotor speed that they have can be extracted as kinetic energy, and it can be injected into the power grid in that way. Another group that will be involved is the microgrid frequency control. So a microgrid is almost a smaller version of the power grid. It's pretty much self-stable, and it will work in an islanded network, it's called. So this is where, say, a small village could have houses which have solar panels on them, and it's pretty much self-sufficient. The power of the village can support the village and its needs. However, you can also connect that microgrid to the main grid when you need to. And doing this, you can then sell any extra energy you have if the power grid needs it, but it can also act as an additional load if that's necessary. Of course, there's a lot more components involved, and this control strategy is quite difficult, but it's one that can be quite powerful if you've got lots of microgrids connected. Thirdly, demand control. Briefly touched on this already. This will be where devices which are on the demand side or the load side of the power grid are disconnected or connected in order to change the frequency. So for example, an electric vehicle can stop charging, your smart washing machine can pause, and other devices like that can also be used. And then finally, the virtual inertia, which is kind of the main topic that a lot of research tries to focus on, is about dealing with that idea of reducing the number of power stations which are being used and then compensating for the inertia loss which happens in the system. So what virtual inertia does, it will be an energy storage system, which is a battery, which connects to an inverter. And then using different control strategies, you can basically increase and inject some power in order to pretend to be the inertia of a power system. The placement of these devices is really important for this. And in general, it's probably one of the most exciting aspects of research in frequency control, I would say. Finally, data-driven frequency responses is also a very important topic for the future. So we've already mentioned reduced inertia and increases in the distribution generation causes faster and larger frequency transitions. And this makes both analysis and control much harder. So phasor measurement units are devices which can record data of the system, particularly stuff like estimating the frequency. And this massively improves the frequency control schemes, both in terms of their efficiency, but also in terms of coordinating the control between different devices. These PMUs provide really valuable information on dynamics. And this can be used in data-driven modeling and control. For example, an emergency control strategy can be used faster because the PMUs are able to estimate the frequency and say the rate of change of frequency to realize that actually the network is crashing and some sort of disturbance or injection is needed, potentially something very serious. So finally, to summarize the relevant research priorities and the future work of this paper, there seems to be 4. The first one is that there needs to be effective control solutions for the power grids with these high integrations of renewable energies. So particularly the islanded microgrid, it has low inertia, and also because it's mainly built up of these renewable devices will have quite significant power fluctuations. So in order to use this in a way that benefits the main grid, like we mentioned in that non-conventional control, there'll be some really serious control techniques which need to be worked out, which will involve coordinating a lot of devices. The second one is the importance of data-driven modeling in the future. So the PMU is a very useful device for parameter identification and estimation. But as the grid is increasing in scale and the devices are getting more and more diverse, the tuning of these parameters and these control techniques is even more challenging. And so the PMUs and data-driven modeling is going to become more and more important. Thirdly, in terms of time delays of communication, a flexible and fast filtering process and algorithms are going to be necessary in order to help with these controls. We mentioned before that time delays can cause frequency instability because the injected power just basically occurs too late, or the signal's sent too late. And so this is where artificial intelligence and machine learning can also play a very significant role in both load forecasting, which is predicting how much load there'll be at a period of time. The classic story is just before EastEnders, everyone turns on their kettle, and that will cause quite a large spike in the power grid. And also it means that using AI and machine learning, you can analyze the future grid in terms of trends and also market prices. And finally, the fourth one is, of course, the cybersecurity requirements in all these different tech devices which are being added. Anyway, so that's quite a fast summary of this paper. But hopefully, if you've got any questions, I'm happy to try and answer them.